As we get to titrations with weak acids or weak bases, we're getting into what you'll see a lot more on the AP exam in free response and in multiple choice. So understanding the graph, understanding the pH at different points, and understanding which chemicals we have a lot of at that point is very important. We'll talk about it a few different times, but really make sure that you pay attention to the details and the key bullet points from this video more than many of the others. So just like the titration of a strong acid with a strong base, the pH starts low because we have an acid. But the pH is not as low because the acid is only partially ionized. There's far less hydrogen ion in solution. After the initial increase in pH, as we neutralize some of that acid, the pH would flatten off. And this flat area here we call the buffering region. The buffering region is where the pH doesn't change very significantly. A buffer, as we'll see later, is something that can avoid a change in pH. So there's a range here where the pH doesn't change by much more than 1 to 2 pH units, kind of from 4 to 6 in this case. That is where, even though we're adding a strong base, our pH change is fairly small. For all titrations, the equivalence point is an important place where the acid and base have neutralized one another. But especially when we're dealing with something weak, the half equivalence point is very important. That's when we've added half enough of our base to neutralize our weak acid. And at that point, this fact is super important. We use this to answer free response, to explain them, and to answer lots of different variations on multiple choice questions. The pH at the half equivalence point is equal to the pKa of that weak acid. So P, whether it's pH or pKa, means that it's the negative log of that thing. So this allows us to make a connection between the hydrogen ion concentration and the Ka of our weak acid once we know our equivalence point and we look at halfway there. At the half equivalence point, the reason that this has happened is we haven't reacted away all of our weak acid. We have reacted away half of our weak acid. So half of the acid has turned into its conjugate base, which means we still have half of our acid, but half of it has gone away. And the reason that this is true is that we have equal amounts of the weak acid still in its acid form and the conjugate base in its ion form. We'll see in the Ka expression how that makes H equal to Ka by canceling out the A minus and the HA on the bottom. And we'll also see another equation that kind of supports and proves this to be true. We still have a rapid rise in pH at the equivalence point because our acid is no longer an excess reactant. The base is becoming the excess. For this, the equivalence point is above 7. So instead of totally neutralizing, the salt that we have produced is basic. The equivalence point's above 7 because the conjugate base of a weak acid is a weak base itself. This is the reaction that supports and proves that when we are at that equivalence point, our HA is gone and our OH we do not have an excess of. We are equivalent, the equivalent amount of HA and OH minus, but that has produced some A minus, a weak conjugate base. That weak conjugate base can accept a hydrogen from water, making hydroxide ions. And then when we keep adding our strong base, NaOH, it becomes excess, and then our pH increases and flattens out. These calculations along here are a combination of stoichiometry and equilibrium. A lot of times we want to define all things weak acid and weak base as equilibrium, but we need to remember that the reaction of a strong acid with a weak base, a strong acid with a strong base, a weak acid with a strong base, or any combination of strong and weak is a one-way reaction as hydrogen reacts with hydroxide to make water. So if we are asked about the initial pH of the weak acid, that is totally an equilibrium calculation. The only thing that is in our solution is a weak acid in water, so we do a Ka calculation. If we are looking at the pH for any other points before or after the equivalence point, there's a combination of stoichiometry and equilibrium. These are less common on the AP exam as math questions. A lot of these will get into more conceptual things, but it is important to know what to do with these. You'll see some practice probably in class from some older AP questions where this was very common. So what's important is if we are before our half equivalence point or after our half equivalence point, but we aren't yet to the equivalence point, we have to think about how much excess acid we still have. So we calculate our initial moles of acid and we subtract away the moles of base that have reacted. That tells us how much weak acid is left in our solution. That's a stoichiometry calculation. Just moles minus moles gives us our moles. And then we have to think about the volume. We now have put two liquids together to create a larger volume. So that new moles over the new liters is our new molarity of the weak acid. Using that new volume with the Ka and the molarity of whatever's left over, we can find the pH. That would be an equilibrium calculation. If you're doing this kind of as a step-by-step A, B, C, D, E problem, you have to think and check, do your answers make sense? The pH would be the lowest when we just had the weak acid, and here it would be higher, but still not as high as what we would see at the equivalence point. At the half equivalence point, the pH is equal to the pKa. That uses equilibrium, and we can support and prove that using the Ka expression, or we can just know that fact. The pH at the equivalence point is based upon how strong our weak conjugate base is. So there's some steps to this that are a combination, once again, of stoichiometry and equilibrium. First, we have to use the total volume of the acid plus the base, the amount of acid we started with and the amount of base we added to get to the equivalence point, to figure out what the molarity of our salt would be. We would also need to know the moles of that, which we probably have looked at in a previous part. Because we're looking at the strength or the reaction of the base, we have to acknowledge that we're not using the Ka anymore. We're using the Kb. So we use Ka times Kb equals Kw. That tells us the Kb for our conjugate base. Then we can use Kb and the Kb expression to solve for the hydroxide ion, and if we're asked to convert that to hydrogen ion and to pH. So if you're asked for the pH at the equivalence point, there's a lot going on here. Stoichiometry, equilibrium. You have to think about the fact that we are now looking at the reaction, and we'll come back up to look at it right here of that conjugate base reacting with water, which is why it's a Kb, because it's producing hydroxide ion. So that one has a lot to it. You could be asked about conceptually or mathematically. After the equivalence point, it is all or pretty much all stoichiometry. Although we do have a weak conjugate base in excess, the hydroxide ion is way stronger than that. So we have to think about how much of the hydroxide is left over. The first part of the hydroxide was used to get the equivalence point. It's only the moles after the equivalence point that are contributing to its new molarity. And then we also think about the total volume, the volume of the acid, plus how much base we got to that point. So it's definitely a limiting excess problem, which is a good way to test your knowledge of stoichiometry, and then still thinking about H plus, OH minus, and pH in terms of those relationships. When you're looking at those, do remember, no matter how hard one of these problems looks or how many steps there are, if you know pH, that means you know H plus. If you know H plus, that means you know OH minus, or any version of that. OH minus can lead to H plus, which can get us pH. So even if we're not sure how we got through some of these other steps, when we know one of those at a certain point, we can connect it to the other. So you'll see with these weak with strong, the math, I've got a lot of parts here. It is very unlikely you're going to be doing all of those on a single AP question, but you may have parts of them that you walk through, and you may also see those as practice problems in class.